Good evening, everyone. Welcome to the class 7 live session on the course Fundamentals of Protein Chemistry. So this is the course taken by Professor Shagota Dasgupta of IIT Kharagpur. I am Srijan Sen, and today I will be taking your week 7 live class session. Okay. So I'm sharing my slides with you all. So last class we basically talked about enzyme, the classification, and the functions of the different classes of enzymes. A little bit about the what actually the importance of these enzymes and how are they different from the chemical catalysts. In today's class, we will be mostly discussing about it's related to enzymes, so it's the enzyme kinetics and inhibition of enzymes. So from the name, if you can understand that last class we talked about what enzymes actually do. In today's class, we will be discussing about they are doing it, but what is the kinetics or what are the kinetic parameters involved in this thing, and what happens when there is a competitive or a non-competitive inhibition taking place within the particular reaction system, that is the enzyme inhibition. So kinetics of enzymes, it follows a zero order kinetics when substrate concentration is high. So zero order kinetics signifies that there is no increase in the rate of a reaction when more substrate is added. So like you have the example is the breakdown of sucrose to glucose or fructose. So the Michaelis-Menten derived equation, so we will directly jump into this we have enzyme plus the substrate. You have K1 as the positive rate of the reaction. You have the complex formation, that is your ES and then finally you get to the enzyme, and the substrate becomes the product. So there are different rate constants. You have K1, that's the forward for the reactant to the complex. You have K3, that's the forward from the complex to the product formation. And then you have the reverse reactions as K2 from the complex to the reactant and product to the complex, that is K4. So you can understand the rate of ES formation. So it's a steady state approximation where the rate of ES is tending to 0, because you do not get the complex in hand. Rather, what you only find is the unreacted reactant and the substrate, and finally the product. So the rate of the complex formation is equal to the total enzyme kinetics minus total enzyme present minus the enzyme with the substrate and multiplied by the substrate. So the rate of breakdown to product is K2ES plus K3ES. Thus, for the steady state approximation, where the concentration of the complex enzyme substrate tends to 0, so this is the equation that's the basis for the Michaelis-Menten algebraic rearrangement and the substitution of Km and Vmax terms. So what does Michaelis constant or Km tell? So basically it's the substrate concentration that produces half the maximal velocity, where Vmax by 2 is known as the Michaelis constant. So when the Vmax, so there is a Vmax value, when the Vmax is just half of its maximum value, then the point at which the substrate, at that particular point of substrate concentration, is known as the Michaelis constant. So there is the significance of Michaelis constant. That's Michaelis constant have been determined for many commonly used enzymes. The size of this constant tells us several things about a particular enzyme, like a small km indicates that the enzyme requires a small amount of substrate to become saturated. Hence, the maximum velocity is reached at relatively low substrate concentrations. A large Km indicates that the need for high substrate concentrations to achieve the maximum velocity. The substrate with the lowest Km upon which the enzyme acts as a catalyst is frequently assumed to be enzyme's natural substrate, though it is not true for all the enzymes. And a Km of 10 to the power minus 7 molar indicates that the substrate has greater affinity for the enzyme than if the Km is 10 to the power minus 5. So there are several things like upon the specificity, the catalytic efficiency of the enzymes can be commented on from this Km value. That is why Km is very, very important. So the significance of Km is to understand the enzyme kinetic constant. It indicates that substrate concentration required for an enzyme to work efficiently. Then low Km indicates high affinity of enzymes towards the substrate, and also the vice versa, because Km is inversely proportional to the affinity. For example, hexokinase and glucokinase, where the Km of hexokinase is low, that is 10 to the power minus 5, whereas Km of glucokinase is high, that is 2 into 10 to the power minus 2 molar. So Km is required when enzymes are used as drugs, because you want molecules to bind with higher affinity to your substrate. For that, it is very important to understand the binding affinity, and from that the constant Km value, Michaelis constant, will give you a lot of idea on. Therefore, it is very important in the therapeutic drug trials. And finally, use of enzymes in immunodiagnostics, like you have the ELISA that requires the Km of enzymes. But that's the Michaelis constant. But you have another very important term, that's the catalytic constant, or the Kcat. So Kcat basically tells you about at high substrate concentration the overall velocity of the reaction is Vmax, and the rate is determined by the enzyme concentration. So the rate constant observed under these conditions is the catalytic constant. So Vmax equals to Kcat into the total enzyme concentration. So Kcat is equal to the Vmax by total enzyme concentration. Where you know about Vmax, you have the total enzyme concentration is known to you, then Kcat can be easily found out. So Kcat basically indicates the maximum number of substrate molecules converted to product per second by the active site. So two important factors are here. It's that the maximum number of substrate molecules have to be converted to the product every second. So based on that, the kcat value is determined. You also know this kcat value by the term of turnover number. So turnover number is very same. It's like how many molecules of substrate are getting converted to the product per second. So the rate constant is the kcat and the term is the turnover number. So the catalytic constant measures how fast a given enzyme can catalyze a specific reaction, describing the effectiveness of the particular enzyme. And kcat is like the unit of kcat is second inverse. So for most enzymes, you will see that kcat or the turnover number is around 100 to 1000 second inverse, even more for fast, efficiently working enzymes. So now we come to the assumption of equilibrium. So this is entirely based on the steady state approximation that I was telling, where you do not know the concentration of the complex enzyme and substrate, and then what you do over here is a steady state approximation. So steady state approximation tells you that you do not get the concentration, or you can never calculate the concentration of the complex so easily. So therefore it is important that we fix up an equation where we might understand that the reactant is going into the intermediate step, that is your complex, and then to the product, but you can neither get the intermediate nor the concentration of it. Therefore the rate of that formation of the complex tends to 0. So there is a factor known as the dissociation constant for the ES complex. So Ks is the dissociation constant. Now there is an assumption that always takes place in equilibrium, that is the forward reaction is much faster than the formation of it's higher. So the rate K minus 1 is higher than K2. The formation of the product is so much slower than the formation of the X complex that we can assume that K is equals to K minus 1 by K1, and we are neglecting the K2 factor over here. So based on the steady state approximation, what do we see over here is like you see you have the substrate concentration that is very high over here, and ES is your intermediate step, and finally you have the product. So in the beginning you have higher substrate concentrations, you are adding enzyme bit by bit, and you will see that the enzyme concentration coming to, so first you add a lot of it, and then with time you're slowing it down, and you're again coming back to the point where, so this is the total enzyme concentration. The substrate concentration starts decreasing over the time and the product increases. But what happens is that you will first see that the complex formation rises, reaches a saturation, and finally it goes down. So therefore you will see that there is just zero displacement across the time axis. So therefore so there is zero displacement across the concentration axis. So therefore the concentration of the complex is tending to 0. Now you will have a lot of equations where you need to calculate the Michaelis-Menten thing. So the total enzyme concentration is equal to the enzyme concentration plus the substrate concentration over here. And on combining a few of these equations, you will see that you come to equation which is very important, where the concentration of the complex is equal to the total enzyme concentration plus multiplied by the substrate concentration divided by Km plus the substrate concentration. So Km, what is that Km? So it's a summation of the for reverse and the reverse reaction of the, so it's K minus 1. So K minus 1 is the complex to the reactant formation rate constant, and K2 is the product formation rate constant. So it's the summation of the two divided by the K1, the forward reaction towards the complex. So now when you simplify this equation, you will see that, so you know the value of Km, you put this value over here and then you try to solve it. So you see you have K2 into substrate concentration, you put the value over here, you try to simplify it, and you get come to another equation, that is Vmax equals to K2 into total enzyme concentration. And additionally, a very important equation, that's the Michaelis-Menten equation, and that you need to always keep in mind, is V naught equals to Vmax into substrate concentration divided by Km plus substrate concentration. So like previously I said that at half Vmax, that is the concentration where that is your Km. So why is it so? Because you put V naught equals to Vmax by 2. So you see over here, so Vmax you get cancelled, you get Km plus S equals to 2S, and after calculating it, you know V naught equals to Vmax by 2, and where Km equals to the substrate concentration. Okay. So the point at which the Vmax is half, that is the substrate concentration, and that will give you an idea about the Km value. Now you plot it over here and you see it. So when you plot it, so the Km is the substrate concentration, where V naught value equals to a half of Vmax. Right, so far so good. Okay. Okay, so the Km widely varies among the different enzymes. So the Km can be expressed as your Km equals to K minus 1 by K1 plus K2 by K1, which is equal to Ks plus K2 by K1. Okay, so as the Ks value decreases, the affinity for the substrate increases, and Km can be a measure for substrate affinity if K2 is less than K minus 1. So the factors that affects the enzyme kinetics is the enzyme concentration, then you have the temperature, hydrogen ion concentration or pH, substrate concentration, inhibitors, product concentration, activators, and the physical agent. So it affects the enzyme kinetics because it affects the activity of the enzyme. So how about the substrate concentration? So you've seen that substrate concentration equals to Km at half of velocity, maximum velocity. So it's a rectangular hyperbola, the Michaelis plot, and the initial velocity when the little substrate is reacted. So the reasons for the three phases of the curve can be interpreted like in the first phase the substrate concentration is low and most of the enzyme molecules are free, so they combine with the substrate molecules. Therefore, the velocity is proportional to the substrate concentration, and at this stage the enzyme reaction is a first order kinetics. Now then you go into the second phase where most of the enzyme molecules are bound to the substrate, so the velocity is not proportional to the substrate concentration, and you will observe a mixed order kinetics. In the third phase, all the enzyme molecules are bound to the substrate, so the velocity remains unchanged because free enzyme is not available, and then you reach a saturation, that's the zero order kinetics, where even if you're adding a lot more of a substrate or an enzyme, then uh, even if you're adding a lot of substrate, then it makes just no sense because it has reached a saturation and there is no free enzyme to bind to it. So now when you actually try to reciprocate the or do the double reciprocal plot of the Michaelis-Menten equation, you get 1 by V naught equals to Km by Vmax into 1 by substrate concentration plus 1 by Vmax. So you see over here that you plot 1 by V naught versus 1 by substrate concentration. Okay, and along the x-axis you will get the minus 1 by km. In the y-intercept you get 1 by Vmax, and the slope is like km by Vmax. And from here you can calculate the substrate concentration at different points. So this is also the Lineweaver-Burke plot, similar to that. So where the slope is Km by Vmax that I have shown over here. So does a double reciprocal plot or the Lineweaver-Burke plot. 1 by V naught is intercept is equal to 1 by Vmax. The extrapolated x-intercept is equal to minus 1 by Km. So for small errors at low substrate concentration leads to large errors in 1 by V naught. So Kcat is equal to Vmax by total enzyme concentration. So Kcat is how many reactions an enzyme can catalyze per second. That's the turnover number. So for Michaelis-Menten kinetics, K2 equals to Kcat when substrate concentration is less than Km. Very little complex is formed, and the enzyme concentration is equal to the total enzyme concentration. And then you will get Kcat by Km as a measure of the catalytic efficiency if you solve the particular equation. So where you have the velocity equal to K2 by Km into enzyme concentration and the substrate concentration. And then you get about the Kcat by Km. Okay. So what you need to do is basically keep these equations in mind, mostly the Michaelis-Menten equation, some of these Lineweaver-Burke plot equations, because these are the two very important plots that will be important when you are solving the questions and doing the assignments and all. There will be so many questions, numericals from here about the V naught, the Kcat, then uh, the Km values and all, and you just need to remember the equation where you have the total substrate concentration that is given, you know the enzyme concentration, and you have to find the Km value, Kcat value, the slopes. Okay, the slope value, then what will happen at the x-intercept, y-intercept, something like this equations will be there. So be prepared for all of these. So any questions still here? Anyone has any questions? I will give 2 minutes for you to figure out, maybe 2 minutes, like for figuring out if you have any questions. Because then after this we will go into the enzyme inhibition. Okay, where we will see how the enzyme gets inhibited, what are the different inhibitors available and all. Any two products. So the question is like, is the reaction of intermediate to product in enzyme catalyze should be reversible? The question is not about it should be reversible or not. It is like it is any two things that are in equilibrium are always we give it a reversible sign. Now the question is basically like, can the product ever go back into the complex? So probably possible sometimes, but for an enzyme catalyzed reaction it is very very difficult, because your enzyme was previously or has been formed or trained, rather trained in a manner such that it does not come back from the product to the substrate. So there is not like you have the product, it's coming back to the substrate, it's something like that. It basically stops at the complex formation. Okay, so the complex is formed, the enzyme substrate complex is formed, and the reaction barrier is so high in the from the intermediate to the product that it does not go to the product. So yes, so the reversible, we say that the reversible reaction is possible, but for most of these chemical reactions, what it's not like a ice changing into water and water back to ice. So these are chemical reactions. So there is nothing such a reversible reaction that can occur. The reaction can basically stop in the enzyme complex formation, and that is absolutely possible. Okay. Okay, so I guess there are no more questions. So, okay, let's go into the second part of this chapter then, that is inhibition kinetics. So, there are three types of kinetics that is known, like competitive, mixed, and uncompetitive. So, from the name, you can understand that where there is a inhibitor that competes with the substrate. So inhibitor competing with the substrate means that the inhibitor has equal tendency as the substrate to bind to the particular enzyme. So you see, you have an enzyme, you have a substrate, it goes into the enzyme substrate complex, you have the product plus the enzyme. The other reaction is also switched on, where you have the enzyme plus the inhibitor, and then you have the rate for the inhibitor, and then you have the enzyme inhibitor, but the substrate does not bind to that particular complex because there is a competition, and the inhibitor has higher affinity for the enzyme than your substrate. So there is no reaction, or from a much more scientific logical term we can tell that you might get a very less product, because this pathway is also on, this pathway is also on, but it depends on like which is a more stable product, and based and higher affinity, that will also determine about the on which side will the La Chatelier principle shift to. So the enzyme kinetics it's more similar to what we saw previously. Here you have the Ki, that is for the inhibitor, the rate for the inhibitor pathway, where Ki is from the reactant to the enzyme inhibitor complex. So that's the rate of formation, which is equal to the enzyme concentration into the inhibitor concentration divided by the complex concentration. And there is a factor that is alpha, so alpha equals to 1 plus inhibitor concentration divided by the Ki, that is the rate of inhibition. So V naught equals to V max into substrate concentration divided by alpha Km plus substrate concentration. So that is entirely the competitive inhibitor kinetics. When alpha is 1, you will see that, so this is like no inhibition is happening. When alpha 2, you see that so with increasing I, you see the slope is actually decreasing. So alpha equals to 1 plus I into like that. So yeah. So over here you see the Km value increases as the alpha value is also increasing over here. So for a Lineweaver-Burke plot, you will see that alpha 1, so you have no inhibitor, and then slope is alpha Km by V max. So Km value So the slope over here increases. Excuse me. So 1 by Vmax remains constant over here. So with increasing inhibitor concentration, slope increases, and you will see the x-intercept also increasing. For non-competitive inhibition, so you mean that there is no competition, so the inhibitor can bind irrespective of whether the substrate is bound to it or not bound to it. So in the complex reaction, it's like anyways there won't be any reaction, but when the substrate is formed, so it does not go into the product, rather it binds with the inhibitor because the binding site is different, the active site is different, and that rate is ki dash. So with the increasing I, you will see that there is no change in the slope of the reaction, and but the x-intercept increases, sorry, it decreases, as well as the Vmax. So 1 by Vmax value, it is increasing. So alpha dash by Vmax increases, minus alpha dash by Km, it is decreasing, and the slope remains the same. The third type is the mixed inhibition, where you can have the enzyme that can bind with the inhibitor, you can have the complex that binds with the inhibitor, and you will have the ESI, that's the enzyme substrate inhibitor complex, or the enzyme inhibitor complex. And for in that case, you see the Lineweaver-Burke plot, you have this, you have so many different patterns that you're observing. So like the slope becomes, where is the slope? So you have the slope that becomes alpha km by V max. You will have the x-intercept as minus alpha dash by alpha km, and with increasing concentration of the inhibitor, you will see that the alpha dash by V max also increases, and your alpha dash by minus alpha dash by alpha km, that also increases. The slope, definitely from the graph you can see that it also increases. So all the three factors are increasing, and you get a middle point, the point at which the lines merge, that is 1 minus alpha dash by alpha minus 1 into km, and the y-axis is alpha minus alpha dash by alpha minus 1 by Vmax. So mixed inhibition is when the inhibitor binds to the enzyme at a location distinct from the substrate binding site. Like I was telling, it has a different binding site. The binding of the inhibitor will either alter the Km or the Vmax, or might be both, which you can see from the equation as well. So alpha was like inhibitor 1 plus inhibitor concentration by Ki, and alpha dash is 1 plus inhibitor concentration by Ki dash. So with the different types of inhibition, you see that when there is no inhibition, you get Vmax and Km. But upon the type of inhibition, so for a competitive inhibition, the Vmax remains constant, Km increases. For uncompetitive inhibition, you see Vmax decreases, Km also decreases. And for mixed inhibition, Vmax decreases, and for Km, most of the cases it remains constant, or sometimes it can increase or decrease depending on alpha and alpha dash values. Okay. So yeah, that's all about the chapter. Any questions on the inhibition portion? So most of these are basically, a lot of equations are there. You will see a lot of questions coming from these graphs, these plots. They ask you what is the value, does Kmax increase, Vmax decrease, Km increases, decreases, these sort of questions, like the Lineweaver-Burke plot, Michaelis-Menten equations, and all. So there will be a lot of questions from this portion. So it's very important that you know these concepts. And then inhibition portions, there will be questions. So any questions? from this portion. So no questions? Okay. So let us go into the practice problems then. So you people first give me an answer and then I will tell you the correct one. Okay. So the first one is enzyme velocity can diminish over time due to decrease in substrate concentration, product inhibition, pH changes or thermal inactivation. Okay, I did not get your question that time. Okay, so are inhibitor and catalytic poison are same term? No, no, no. We cannot tell that. So the two, why they are not same? Because uh, see, catalytic poisons act as inhibitors, but not always. But inhibitors function very differently. So it is not like it is meant to be an inhibitor, it can also be a binder for another protein or another substrate or so. But when you tell it as a catalytic poison, it's a very general term. Like catalytic poisons means it affects every enzyme or every it affects the activity of every enzyme. But inhibitor, for example, you say inhibitor X, it can bind to your enzyme X like that, but probably it's an activator for enzyme Y. It is good that your inhibitor is having an affinity for enzyme X or might be having for enzyme Y. So in one case it might act as an activator, the other case it is acting as an inhibitor because it binds the same active site of the protein, so the actual substrate cannot come and bind. Okay. Yeah. So what's the question then? Enzyme velocity. Okay, so the question, enzyme velocity can diminish over time due to decrease in substrate concentration, product inhibition, pH changes, thermal inactivation. What will be the answer? See, yes, you can actually see that most of these options are actually very correct. So decrease in substrate concentration. So when you decrease the substrate concentration, the velocity, maximum velocity decreases. Product inhibition means the substrate cannot form a product, so the activity of the enzyme decreases, leading to decrease. The changes in pH can hamper the enzyme activity. And finally, the thermal inactivation, that is also correct. Okay, so yeah, just give me 2 to 3 minutes. I will be just back. In the meantime, you can just go through these questions and try to solve them. I will just be back. Okay, so you try to do this. What is the first one? The reaction source represents formation of an enzyme substrate complex followed by breakdown and release of product P. The rate of ES breakdown will be. So what will be the rate of ES breakdown? So you see over here for so this is the step. So here you have the ES forming. So that is K minus 2 K minus 1. So K minus 1 ES, that is, and K2 ES, but they have not said actually that K2 equals to K1. Okay. Okay, yes, A is the correct option. Right. So you see over here, so this is the K2. So from E and so it's the interface breakdown will be. So this is. No, I feel that there is something that is not correct with the options. So the actual one should be K minus 1 into enzyme substrate complex concentration plus K minus 2 into enzyme concentration and the product concentration. So that is the correct, which is not given over here. And they have also not mentioned about whether K2 equals to K minus 2 or not. So it's difficult to. Okay. So the next one is in a mixed inhibition, the enzyme inhibitor complex EI has a dash affinity for dash compared to that of dash. So is it a lower, higher, is it the enzyme substrate or the substrate enzyme? What is it? So in mixed inhibition, the enzyme inhibitor complex EI so I got one answer, maybe, yeah. B, okay, I got C, right. Yes, so B is correct. It has higher affinity for the enzyme compared to that of the. It has higher affinity for the substrate compared to that of the enzyme. Yes, that is correct. And also it has lower affinity for the enzyme compared to that of the substrate. So A and B both will be correct over here. Okay. Now, derivation of Michaelis-Menten kinetics occurs when there are multiple substrates. Substrates binding is irreversible. K2 equals to K cat and enzyme displays cooperativity. So when do you see this? There are multiple substrates, substrate binding reversible, K2 K cat, and the enzyme displays cooperativity. So you will see deviation from Michaelis-Menten kinetics. When there are multiple substrate, it becomes complex, and it is actually based on a single substrate binding model to the enzyme. Substrate binding is irreversible, so the Michaelis-Menten model, it assumes a rapid equilibrium between the enzyme substrate and the substrate complex. So irreversible binding would lead to a different kinetic profile. K2 equals to K cat is absolutely fine, and the enzyme displays cooperativity. So one substrate molecule affects the binding affinity of the subsequent substrate molecule, so that will be deviation from the Michaelis kinetics. The next one is in competitive inhibition, and inhibitor binds to an enzyme at a site other than the active site only to the substrate, reversibly at the active site covalently to the ES complex. So which one is correct over here? In competitive inhibitor, where does the inhibitor bind? So option A says to a site other than the active site. It is incorrect because binding at the site other than the active site describes non-competitive or allosteric inhibition. So it binds at the active sites. The option B is also incorrect because the inhibitor binds to the enzyme, not the substrate itself. And option D is also incorrect because competitive inhibitors bind to the free enzyme, not a covalent bond with the complex. So covalent binding is characteristic of irreversible inhibitors. So option C is the correct one over here. Okay, the next one. Which kind of inhibition is depicted in the diagram shown? So you are seeing a certain kind of an inhibition. You have to tell what kind of an inhibition are we actually seeing. So the last one, it was C. Yeah. So what kind of inhibition are we observing? So you have the inhibitor binding to one side. Yes, it's a mixed inhibition. Correct. Because you see it can bind to the inhibitor and stop the substrate from binding, or when the substrate binds, the inhibitor binds, then there is no activity. So it's a mixed kind of an inhibition. Now, what is not true for an isoenzyme? So which of the thing is not true for an isoenzyme or isozyme? So what are isozymes? So isozymes are basically uh, different forms of an enzyme that catalyze the same reaction, but they differ in their amino acid sequence. So what is not true for an isozyme? So these are the same forms of enzyme but have different amino acids sequence, and they vary in the chemical and physical properties. They regulate a little bit differently, but they do not have the same km values because they regulate differently, so they do not have the same km values. So option B is incorrect. Now, when a product accumulates in a cell beyond an optimal amount, it's produced is decreased by the inhibition of an enzyme involved in its synthesis. After the product has been utilized or broken down and its concentration thus decreased, the inhibition is relaxed and the formation of the product resumes. This type of a mechanism by which the concentration of certain cell constituents is limited, what type of inhibition is this? D, feedback inhibition. Yes, that is correct, because you are getting back a signal like this is what I do not need, so you can stop down the mechanism, and so it's a feedback inhibition. That's correct. Okay. Now, in Michaelis-Menten kinetics, Km is defined as, so how do you define Km? Concentration of substrate required to reach maximum velocity, concentration of enzyme required to reach maximum velocity, or concentration of substrate required to reach half maximum velocity, concentration of enzyme required to reach half maximum velocity. So it's simple. So Km equals to substrate concentration when Vmax is half. So C. The advantage of using Lineweaver-Burke plot is it linearizes the Michaelis-Menten equation, easier to extrapolate a straight line. The errors in Km and Kmax, Vmax is small. Important parameters can be determined from the two intercepts in two axes. Which is correct? Which of these are correct? So if you look into the options, all of these are actually correct. So all the options are correct. Okay, we will not go into this one, right? Okay. So for competitive inhibition, the maximum velocity is obtained at. These are some quick questions. So for competitive inhibition, the maximum velocity is obtained at. Yes, that is correct. Option B, at increased substrate concentration. So in competitive inhibition, the inhibitor competes with the substrate for binding at the active site. So increasing the concentration can overcome it. The next one is with increasing concentration of inhibitor, the Km value increases in case of. So in which case does the concentration of inhibitor, with the increase in the concentration of inhibitor, the Km value increases? Yes, that is also correct. Competitive inhibition. So the inhibitor increases the apparent Km value, meaning that more substrate is required to reach half of Vmax. This is because the inhibitor is competing. Okay, that is correct. In Lineweaver-Burke plot, the y-intercept gives you. So which of it gives you the y-intercept? So from the y-intercept, what do you get? Vmax. V. What is this? B. 1 by Vmax, yes, that is also correct. 1 by Vmax, that's the y-intercept, and the x-intercept is minus 1 by Km, Right, and the last one is during non-competitive inhibition, the inhibitor binds to the site which is called. So what do you call the site where the inhibitor binds to the site for a non-competitive inhibition? That is the allosteric site. Okay, so in non-competitive inhibition, what happens? The inhibitor binds to the allosteric site that is distinct from the active site. So this causes a conformational change, reducing the catalytic activity and the specificity for the substrate to go and bind over there, and it lowers the Vmax, but the Km does not get affected. Yeah. So yeah, that's all. So nothing else is there for today. Any questions you guys have? No questions then? Okay, then thank you very much for joining. We will again meet in the next week.